So for example, y belongs to r, to r. In second part of the class, of the lecture, of the material, is focusing on binary values of y, or categorical values of y. Instead of taking real values, y is taking binary or categorical values. In this scenario, there are some models to be performed, because multiple linear regression is no more valid. It is not suitable and appropriate for analysis of regression models where y is continuous. So when y is binary, for instance, you need to run you have the choice between running two types of regressions: linear discriminant analysis and logistic regression. Okay? Or generally speaking, nonlinear regression. Under linear discriminant analysis, you need to recognize the equation, because under linear regression there are two regressions. The first one for y is equal to 0, and second one for y is equal to 1. So the starting point is that y at time t is equal to 0 or 1. Yt is binary. To regress yt, which is binary, on several x's, you cannot use multiple regression analysis, because assumptions are no more valid under multiple linear regression. So you need to perform linear discriminant analysis or nonlinear analysis, regression analysis. So let's look at linear regression analysis. Under linear regression analysis, you need to recognize equation for y is equal to 0, and equation for y is equal to 1. This is the first thing. The second thing is that you need to evaluate the goodness of fit of the regression. To do so, you need to look at Hosmer statistic. Okay? The second model is the nonlinear regression, and the nonlinear regression can take two forms: the logit or logistic regression and the probit or probabilistic model. Under these models, you need to be able to recognize the equation. Okay? For example, under logit, yt is equal exponential of minus beta 0 plus beta 1x. Okay? And for probits, the probits, yt is equal to 1 over 2 pi, root of 2 pi. Distribution. Under logit and probit, to Wold statistic, and Wold statistic is testing Wold. This is Wold W, sorry. So Wold statistic is testing the null hypothesis that all coefficients are equal to 0, versus the alternative one that one of the coefficients is different from 0. So this is Wold test used to test the global null hypothesis of the model. It is similar to the tests of Fisher applied to multiple linear regression, where YT is continuous. The second one, you need to look at individual hypothesis tests, whether each single coefficient is significant or not. By the way, the final will be very similar to the midterm, except that you got results from LDA, logistic, probit, and you need to explain results, argue whether the coefficients are significant or not significant, argue whether the model is globally significant or not, and so on. Goodness of fit, for goodness of it, so for individual hypothesis tests, we need to look at the p-value of the chi-square. For logits and probits, to check if a specific coefficient is significant, you need to look at the p-value of chi-square. A p-value less than 5% means that the coefficient is significant, otherwise it is not. You need to look at goodness of fit. For goodness of fit, you need to look at Hosmer tests. Okay? To compare models, you need to look at Akaike, you need to look at Schwartz criterion, you need to look at -2 log likelihood. These three statistics are reported by SAS AG. So the best model is the one with the lowest values of Akaike, of Schwartz criterion, and of -2 log likelihood. In equations, so now look at this example where we run a full model under logistic regression, okay? Under logistic regression. So we got criterions of Akaike, Schwartz, and -2 log likelihood. When intercept where y, when the probability of y is regressed only on intercepts, and also same thing when y is regressed on intercepts and x's. X's are chord covariates. We need Akaike, Schwartz, and -2 log likelihood to compare the models, to compare a full model versus a reduced model. The best one should have lowest Akaike, lowest Schwartz criterion, and lowest -2 log likelihood. So let's look at global goodness of fit of the model. We got world, statistic world, having a p-value less than 0. Less than 0. And the world, the null hypothesis to test is the following: H0, all coefficients are equal to 0. H1, not all coefficients are equal to 0. We call this world test for overall significance of the model. So we call it world tests for overall significance of the model, of the regression model. Okay? We call it world test for overall significance of the model. So if p-value of world test is less than 5%, then you reject the null hypothesis, stating that all coefficients are equal to 0. Otherwise, if a p-value of world is larger than 5%, then you accept the null hypothesis, stating that all coefficients are equal to 0. So in this example, the decision is to reject H0. Why? Because sorry. Why? Because p-value is less than 5% significance level, then you reject H0 and you accept the alternative one, stating that not all coefficients are equal to 0. Any questions, please? Okay. Now let's look at the coefficients. We got intercepts having p-value less than 0, so it is significant. Ours having a significant p-value. Effort's coefficient is also significant because p-value is less than 5%. Loss coefficient is also significant, p-value less than 5%. And satisfaction having a p-value less than 5% means it is significant. So the only factor or the only explanatory variable which is not significant is female, with p-value equal to 0.6943, larger than 5% significance level. Okay? Logistic regression, mathematically, we need to write down the mean of y given x's, where y is binary variable. So y is binary variable is equal to p. So the mean of y given x is equal to p. Under multiplying integration, mu of y given x is equal to b0 plus b1 x1 plus b2 x2 and so on. But under logistic regression, the mean of y given x is equal to probability p. And this probability p is equal to the probability of y is equal to 1. Okay? The function, this function is called a logistic function, and it is given by the following formula, where the mean of y given x is equal to 1 over 1 plus exponential of minus beta 0 plus beta 1 x1 plus beta 2 x2 and so on. So in the exam, I will ask you to write down the logist estimated regression. So the logist estimated regression, you need to write is as follows: probability that y is equal to 1, where y indicates satisfaction, is equal to 1. You need to write down this equation and replace beta 0 by its value and each beta by its specific value and corresponding x by its name. So probability of y is equal to 1 or satisfied is equal to 1 because y is named satisfied is equal to 1 over 1 plus exponential of minus intercept plus beta 1 multiplied by hours plus beta 2 multiplied by efforts plus beta 3 multiplied by loss plus beta 4 multiplied by satis counts plus beta 5 multiplied by female. So be sure that in the final exam, I will ask you to write down the logistic function, and you need to be able to write down this equation, mathematical expression, and replace the b's by their respective values and x's by their respective names. Interpretation of the coefficients. This is something I missed from the class last lecture, but it's also a good time to go over it. In the final exam, you may use your class note to answer questions. Interpretation of the coefficients of logistic regression. Let's start by defining an odds ratio. The odds ratio is equal to P over 1 minus P, where P is the probability that Y is equal to 1, and 1 minus P is the probability that Y is equal to 0. Okay? So we can write down the log function or the log probability as follows: L is equal to log of P over 1 minus P, where P is equal to probability of Y is equal to 1, and 1 minus P is equal to the probability of Y is equal to 0. And this is the linear form of the regression. This expression is the same as this one, is equivalent to this one. This is the logit estimated regression, and this is its linear form. How we get this linear form? By applying log to both sides of this equation. If you apply log of probability of Y is equal to 1 to left side, and apply log to the right side, you end up with this expression. Log of probabilities is equal to log of exponential. Log exponential is equal to the equation within the exponential. Interpretation, so this is the log estimated, the logistic estimated equation, and this is the linear form. The linear form. We got it by applying log to both sides of the equation. Interpretation, for 1 unit increase in hours, so this is coefficient of hours, sorry, so this is the coefficient of hours. So for one unit increase in hours, the log odds of being satisfied increases by 0.6453. So when hours increases by 1 unit, the log of odds, the odd is P over 1 minus P. So the incidence will be on log of odds, will be on the ratio of log ratio of probabilities. 1 unit increase in hours yields to an increase by 0.6453 in log of odd ratio. For the second one, for 1 unit increase in efforts, this is efforts, the log of odds, meaning the log of P over 1 minus P, of being satisfied increases by 0.0774. For loss, for 1 unit increase in loss, the log odds, meaning the log of P over 1 minus P, decreases by 0.1803 because we got a negative number. This is a negative number. Also, for 1 unit increase in satiscounts, the log odds or log of ratio of probabilities, log of probability of Y is equal to 1 over probability of Y is equal to 0, increases by 0.6543. And finally, being female versus being male, the log of odds or log of probabilities, probability of Y equal to 1 over probability of Y equal to 0, increases by 0.0802. This is the interpretations. I want you to get knowledge of it for the final exam, because in final exam, I will ask you to interpret this is output from logistic regression. I will ask you to write down the log estimated equation, logistic estimated equation. Then I will ask you to write down the linear form of the logistic equation. Then I will ask you to interpret the coefficients of the independent variables, and also to check if they are significant or not. So interpretations are given there, and if they are significant or not, you need to look at their respective p-values from chi-square. Okay? For this model, we got a ROC curve. The area under the ROC curve, this is the area under the ROC curve. So this is the area This is the area under the ROC curve. The ROC curve is this one. This concave function is the limit, is the ROC curve, and it is limited by diagonal line, which is of 45 degrees. Diagonal function, diagonal line. Okay, so this area under the curve is equal to 0.9254. For a very good model, an accurate model to classify y, to distinguish between y equal to 1, y equal to 0, area under the curve should be equal to 1. Of course, we get Akaike, Schwartz, minus 2 log likelihood. We got Wald. Let's look at Wald first. Wald is testing the null hypothesis that all coefficients of regression are equal to 0. Against alternative one, that not all coefficients are equal to 0. The decision is to reject the null hypothesis since the p-value, this p-value is less than 5% significance level. So final exam will ask you to write down the estimated longitudinal regression from the reduced model, for example. So you need to write probability of satisfied, where satisfied is y. This is y. This is basically y. So satisfied, or y is equal to 1, is equal to 1 over 1 plus exponential of minus intercept plus B1 hours plus B2 efforts plus B3 loss plus B4 satiscounts. The interpretation is like the previous one. One increase, for example, in hours will lead to an increase in log of odds, meaning log of probability of y is equal to 1 over probability of y is equal to 0 by 0.6439. One increase in effort by 1 unit will yield to an increase in odd ratio by 0.0775. One increase in loss by 1 unit will yield to an increase in odd ratio by 0.1807. And finally, one increase in satiscounts by 1 unit will yield to an increase in log odd ratio by 0.6553. We got also the ROC curve. So we got also the ROC curve, the area under the ROC curve. The area under the ROC curve is equal to 0.9255. By the way, in final exam, when I ask you to write down the linear form of this, you need to write log of P, probability of y is equal to 1, is equal to B0 plus B1 hours plus B2 effort plus B3 loss plus B4 satiscounts. So let's get to goodness of fit. Evaluate goodness of fit. We got a good fit under the null hypothesis, not good fit under alternative 1. The p-value, so the p-value is equal to 0.1658, which is larger than 5% significance level. So you accept the null hypothesis, stating that the model is good. Yes, it is, since the p-value is larger than 5% significance level. Now let's get to some serious stuff. We need to compare the two models, full model versus reduced model, in terms of classification performance. For instance, so in terms of classification performance, logit reduced model outperform logit full model in terms of ROC. So the ROC from the reduced model is 9255 against 9254. So the reduced model is showing a slight improvement in area under the ROC curve, meaning that the reduced model is better in forecasting probability of y equal to 1. So in terms of fits, in terms of a linear or nonlinear approximation, which model is best? Is it the full model or reduced model? What do you think? Which one is the best? In terms of fits, the reduced model is better because it is showing Akaike lower Akaike and lower Schwarz criterion. So logist reduced model shows the lowest Akaike and lowest Schwarz criterion. So based on these two performance metrics, reduced model is better in fitting probability of y equal to 1 compared to full model. But if we look at Maestro log likelihood, we conclude that full logit model is better because it has the lowest Maestro log likelihood. So 610, 22.8 against 610, 38.2. So in terms of Maestro log likelihood, the full model is good in fitting y compared probability of y equal to 1 compared to reduced model. But finally, the decision is to pick the reduced logit model. Why? Because we got two criterions against one. So it wins the fight against full model since it has both Akaike and Schwarz lower compared to full model. Any question? Now let's look at the probit model. Probit model. In the probit model, the nonlinear function used is normal distribution. For logit model, we use logistic regression, logistic distribution. For probit, we use normal distribution. So for full model, we got Akaike, we got Schwarz, and we got Maestro log likelihood. And we got also world p-value is less than 5%. It means that the model is highly significant, meaning that at least one of the coefficients, one of the explanatory variables coefficients is different from 0. So the decision rule is to reject H0 since the p-value, this one, is less than 5%. So we got estimation results from probit model. So we got intercept significance, hours significance, effort significance, loss significance, satiscant significance. However, female coefficient is not significant. And by the way, under probit model, we assume a normal distribution in x's. Okay? So meaning that y of x is equal to 2 pi minus 0.5 exponential of minus x power of 2 over 2. This is mathematical form of normal distribution. The probability symmetry interrogation model is written as follow. This equation is exactly the same as this one, except that we replace zeta by b0 plus b1 x1 plus b2 x2 and so on. So we get 2 pi minus 0.5 exponential of minus 0.5 beta 0 plus beta 1 x1, beta 2 x2, beta 2 x3, beta 2 4 x4, beta 5 x5. Now, how to interpret the results? So, contrary to logistic regression, interpretation is slightly different. So, let's first apply a log to both sides. We get p 1 over 1 minus p is equal to beta 0 plus beta 1 x1, beta 2 x2, beta 3 x3, beta 4 x4, and beta 5 x5. This is the linear form. So this is the nonlinear form or the original form of the Probit model. This is the linear form of the Probit model after having applied log transform to both sides of the equation. You end up with this linear form. Interpretation is slightly different. For 1 unit increase in hours, the odds of being satisfied increases by 0.3435. So for logits, we got the log of odds. Under the Probit model, we got simply the odds, not log of odds. So under a logistic, we got the log of odds increases, log of odds increases, log of odds decreases, log of odds increases. But under Probit, that assumes normal distribution in x's and y, we got the odds increases, not log of odds, but odds increases, odds increases, odds decreases, odd increases, and so on. Do you have any question? The ROC curve, now let's compare the two models. The area under the ROC curve so the area under the ROC curve is equal to 0.9254. This is the area under the ROC curve. Hadamard-Lim test shows a p-value of 0.1309, meaning that the null hypothesis that the model is good, is showing a good fit, is accepted. So H0 is accepted. For the reduced model, we get world equal to 0, having a p-value less than 0, meaning that, or meaning that 5 or less than 5% significance level, meaning that the model is significant. So H0, stating that all coefficients are equal to 0, is rejected, and alternative 1 is accepted. Intercept is significant. B1, coefficient of hours, significance. Coefficient of effort, significance. Coefficient of loss, significance. And coefficient of satisficance is also significance, as the respective p-values are smaller compared to 5% significance level. So from this table, we can write down the probit estimated regression for the reduced model. So the probability of y is equal to 1 is equal to pi root of 2 pi exponential minus 0.5 multiplied by beta 0 plus beta 1 hours plus beta 2 efforts plus beta 3 loss plus beta 4 satiscounts. So be sure in final exam we ask you to write down the probit estimation regression and also the linear form of the probit. To write down linear form of the probits, you need to apply log to both sides of the equation and you got linear form. This is the ROC curve area and the ROC curve for the reduced model. Hosmer test shows a p-value of 0.1780, meaning that the model is showing a good fit. The model has a good fit to approximate y or variations in y. Comparison of models. So in terms of classification performance, if you look to the probit full model, so the probit full model outperforms probit reduced model in terms of ROC. Yes, let's look at ROC. And the reduced model is equal to 0.9253, 9253, 9253 against 9254. So the full model is more able to predict y, or probability of y is equal to 1 compared to reduced model. But it's not a big deal because the two ROC curves are very similar. There's a difference of 0.001, not a big or large difference. So in terms of good of fit, reduced model is showing a better good of fit for y, or probability of y is equal to 1, because it has the lowest Akaike, 618 against 620, Schwartz criterion, lowest one, 642 against 649. But in terms of -2 log likelihood, it turns to be that the full model is showing a better one. -2 log likelihood and the probit full model is better than that of the probit reduced model. So we got 608.563 against 608.734. So by looking to statistics of goodness of fits, we got two statistics indicating that reduced model is better. So we take the reduced model. Two statistics against one. Not a big deal, it's easy to take the decision. This is the example from linear discriminant analysis. For the full model, in the exam, you need to write down equation where when y is equal to 0, and an equation for y equal to 1. So when I give you this output, you need to be able to write down y two equations. because linear discrete analysis is based on two regressions, on two different regressions. One regression for y equal to 0, and the another one for y is equal to 1. So this is equation for y equal to 0, equation for y is equal to 1. We get the constants, beta 1, beta 2, beta 3, and beta 4. So for beta 1, for a group 0, or y is equal to 0, we get beta 1, beta 0, plus beta 1, female, plus beta 2, effort, plus beta 3, loss, plus beta 4, 5 satiscounts. For group 1, we got B0 of group 1 plus beta 1 female of group 1 plus beta 2 of group 2 of group 1, and so on. So this table is showing the misclassification rates for for linear discrete analysis, where y is equal to 0 and when y is equal to 1. So the error rates for y is equal to 0 is 0.1871, and the error rate for y equal to 1 is 0.1628. So if I ask you the following question in the final exam, is linear discrete analysis better in classifying y equal to 0 or for classifying y equal to 1? What will be your answer? If I ask you whether linear discriminant is good in classifying y equal to 1 or require y equal to 0, what will be your answer?
Y equal to 1.
Exactly. This linear discrete analysis model is appropriate for classification of y equal to 1 because error rates associated with y equal to 1, this one means that y equal to 1 is 0.1628 less than 0, the error rate from y equal to 0. Error rate from y equal to 0 is 0.1871, larger than that from y equal to 1, which is equal to 0.1628. So this model is suitable to classify y equal to 1, not to y equal to 0. Let's look at the results from reduced model. For this model, we got equation for zeros for y equal to 0 and equation for y equal to 1. Okay? This is the written form of y equal to 0, mean that y equal to 0, when y equal to 0, we got group 0, B0 plus B1 effort plus B2 loss plus B3 satiscounts. We got equation for group 1, beta 0 plus beta 1 effort plus beta 2 loss plus beta 2 satiscounts. Sorry. So for the reduced model, if I ask you again same question, is the reduced model from linear discrete analysis better in classifying y equal to 1 or y equal to 0? What will be your answer?
Again, y equal to 1.
Again, y equal to 1. So linear discrete analysis and the reduced model is better in classifying y equal to 1. Now we need to compare linear discriminant analysis of full model against the one from reduced model. So accordingly, the one from reduced model is better since it has the lowest misclassification rates. Where is this misclassification rate? Is this one? This is the global misclassification rate. It is equal to 0.1695 against, so 1695 against 1695 against 1750. So the error from a full model is 0.1750, and the error from reduced model, LDR was 1695. So, of course, LDR reduced model is the best one in distinguishing between y equal to 1 and y equal to 0. Interaction variables are there some equations regarding probits and logits? Okay. Interaction variables are suitable to check whether two regressors or two inputs or two explanatory variables are showing an interdependence in level, meaning that if you expect that the level of x1 is dependent on level of x2 and that level of x2 is dependent on level of x1, then include, please do include interaction term in your regression model. So this is a model where y, which y is loss. So the dependence variable is loss, and it is regressed against intercept hours and efforts. Okay? So we got hours significant, we got effort significant, VIF is okay because it is less than 10, so there is no multicollinearity in the regression model. And Darwin-Watson is 0.314, meaning that there is a problem of autocorrelations in the errors since Darwin-Watson is close to 0. Okay? Test for normality. Test for normality, we got Anderson, p-value is equal to 0.005, less than 5% significance. So we do reject the null hypothesis of normal distribution. So the errors are not normally distributed. And let's look at interaction term. Suppose you believe that interaction term matters. So include it into the regression, and we got an interaction term significance. A p-value is equal to 0.0362, less than 5%, meaning that the y, which is loss, is dependent in hours, and that the level of hours is also dependent on the level of efforts. Or alternatively, y dependent, which is loss, is dependent on level of efforts, and that level of effort is dependent on the level of efforts. This is indicated by p-value, which is highly significant. Now, how to interpret the coefficient of interaction variable hours by efforts? So interaction means that the effect of hours or loss is different from different values of efforts. So for each value of effort, we got a different impact of hours on loss. By changing efforts, we get different level of hours impact on Y. The unique effect of hours on loss is not limited to B1. So this is B1. This is the B1. So the unique effect of hours on loss, it is not limited to B1, but it is also limited to the interaction effort, which is B3. And also, the loss, the impact of effort on loss, it is not limited to beta 2, but it is also limited, affected by beta 3. So the unique effect of hours on loss is not limited to beta 1, but also depends on the values of beta 3. Also, the unique effect of hours on loss is represented by everything that is multiplied by hours in the model. For example, beta 1 plus beta 1 so the impact of hours on loss is globally beta 1 plus beta 3 efforts. So it's equal to beta 1 plus beta 3 efforts. Because the interaction term is significant. Beta 1 is now interpreted as the unique effect of hours on loss only when effort is equal to 0. So beta 1, so this is the unique effect of hours when effort is equal to 0. And this one is the unique effect of efforts when hours is equal to 1. So globally speaking, or generally speaking, this is the partial effects. This is the partial effects of hours on loss. This is partial effects of efforts on loss. And this is the combination effect of hours and efforts on loss. So please do use these interpretations for the final exam, because I may ask you to interpret the interaction terms in final exam. So the review is done. Do you have any questions?
Professor?
Yes?
Just to confirm, we won't have to use SAS-EG? We'll have the results already?
Yes, more like, yeah, we give you results of SAS-EG and you need to interpret the results.
Okay, and this will be uploaded.
Or maybe for some exercises, I can give you data and you run models and interpret results. So both scenarios are plausible.
Will this file be uploaded, Professor?
It is already uploaded on Moodle. So please go to Moodle to download the file. Check Moodle, you will find it.
Thank you, Professor.
Thank you. Other questions?
Yeah, actually, I have a question. It's about the assignment number 2. So for when we do backwards elimination, forward selection, and stepwise selection, we're asked to calculate the standard error. Well, we're asked the standard error of the chosen equation, and the way my group and I did it was by adding the standard error of the intercept and the variables, but we're not 100% sure if this is correct.
No, standard error of the equation is already shown on regression on SAS outputs.
We
Let
don't
me-
see it though when we do the backwards elimination, the forward
Huh?
selection and stepwise selection. I don't know if we're missing a step or something when we're running the model because we don't get the error. That's why we were adding it.
If you'd like, we can share our screen, just show you
Yes,
what
yes.
we're getting. Okay.
Okay.
Could you enable it, please?
Yes.
Thank you. Can you see my screen? This is for backwards elimination.
Okay.
And when we go down, this is like the conclusion, the last step. And we don't see like the standard error, we just see this. And this is what we did. We added these three up, but I don't think that's the correct way. I'm not really sure because I don't see anything else.
But, okay, I will give you hints and you need to do extra effort to find it. The hint is that the standard error of regression is analysis of variance, check something there. Okay?
Okay, so we use this like table to like find the standard
Yes.
error. Okay,
If you are looking for the standard error of the global model, you need to go to analysis of variance table and you will find it. It is somewhere. It is there somewhere.
okay,
Okay?
we'll look for it. Thank you. Also, just one last thing, like quickly, when Parisa showed us about the interaction effect, she was telling us to use the line plots like this, and if they cross, it means that there is an interaction effect present.
Exactly.
Okay, because these graphs show us like that there is, but when we did the hypothesis test, like the p-value was low, and it said basically that there was no interaction effect.
If the p-value is low, so the p-value mean large,
Oh,
not
yes,
low.
sorry, yes, the opposite, yes.
Opposite, okay.
Yes.
If p-value is large, so the interaction effect is not there, is not significant. So run your regression without interaction effect.
And that was my question, because Parisa didn't show this, how to remove interaction effect.
It's very easy. Run your regression without interaction effect, and then run another regression with interaction effect, and evaluate whether the interaction effect p-value is significant or not.
Okay,
We include interaction effects only if we believe that the interaction effects matters. Otherwise, we don't need to include it.
okay,
Okay,
thank you.
but to be sure, run one regression without, the other regression with, look at p-value.
Thank you.
Thank you.
Sir, I have a question.
Yes.
Yeah, I couldn't open data in SASH and I asked Parisa, and she couldn't figure out what happened. I mean, now does the lab is open? Or is there any computer we can borrow from university or school?
Are you asking about if the lab is open?
Yeah.
I think so. You can get there.
So
I think so. You can get there.
So now it's open, the campus lab?
I think it's yes. I'm not sure, but I think it's yes. But look, you don't need to go to the campus. You don't need to go to the lab. You can get connected to the lab remotely.
Yeah, but just I couldn't figure out how was the status.
Okay, I don't know how to do it, but send email to Help Concordia, or ask Parisa to show you how to do it. But you can stay home and get connected to the lab remotely. You need to go to the lab physically.
Okay, I will ask Parisa.
Okay,
Thank you.
thank you. Other questions?
Professor,
Yes.
for the project, it's just a PowerPoint, right? We don't have to do like a written report.
No, just the PowerPoint.
Okay, thank you.
The report will be your PowerPoint.
Thank you, Professor.
Yes, thank you very much. Other questions, please?
Are we submitting the PDF at the same time as the PowerPoint, like the day we present?
Yes, I will create a folder where to deposit your presentations.
Okay. Should we write in the comments like a general idea of what we're gonna say, or is it okay if it's blank?
Comments on what?
Like on PowerPoint, how you can write like comments, like notes under each slide?
You write the comments or I write the comments?
No. If like you wanted us to like add in the comment section of each like slide of the PowerPoint, if you wanted us to write like kind of not a script, but like a general idea of what each slide means.
Yes, I would prefer to.
Okay, perfect. Thank you.
Okay, thank you. Other questions? So thank you for taking the course, and we meet next Wednesday for presentations. And if you do have any questions regarding your projects,